we'll start here with the free body diagram. We need to find out what exactly all forces are acting on our car here. Okay, so take a few seconds and get it written down, and then we'll look at our free body diagram. Here's my system or my car. I've got first, I'm going to look at my applied force or whatever's being applied here to our car. Force of 2,000 newtons acting at an angle with 60 degrees with respect to the horizontal. With respect to the horizontal means above the normal or the positive x-axis. So it always means north of east. That's what to the horizontal means. Okay, so let me move my dot here a little bit. Okay, so here's our 60 degrees. It has a value of 2,000 newtons. Okay, so we've got some force that's being applied at an angle. What other forces are acting on this car? Michael? It doesn't tell us anything about friction, so we could ignore friction unless it tells us to include it. Good point, though. Gravity. And what do we label gravity? F sub g, good. And what other force has to be acting on it? The normal force, good, because it's on a surface. Our car's not floating in the air here. Okay, we've got some normal force. So now let's break this applied force into components. Right, we don't like dealing with things at an angle, so we have to break it into components. If I'm going to name this side right here, I'm going to call it F applied. So I always just use F and then an APP for an applied force. You can call it a push or a pull or whatever you want. That's fine. But it's going to be in the y direction. Okay, so it looks like FAPI. You'll see it a lot. Okay. And then for this side right here, I'm going to call it F applied X. Okay, so here we want to find the mass of our car. That's our overall goal. Tell me this, the car that's accelerating, it has a rate of 10 meters per second. Is that acceleration in the vertical direction or the horizontal direction? Horizontal direction. So our acceleration's in the horizontal direction. Does our car have any acceleration in the vertical direction? No, because it's at rest. It's not moving up and down at all. It's not bouncing, it's not doing anything in the vertical direction. We're only looking at horizontal acceleration here, which means we only care about our horizontal forces. Okay, so when we do problems like this, you've got to make sure you pay attention to what direction is it moving. Is it moving horizontal? Is it moving vertical? And only look at those forces. Those are the only ones that you're concerned with. Okay, so we're looking here at our horizontal acceleration. So you can say A in the x direction, if you want, is equal to 10 meters per second squared. Okay, you don't have to label it in the x direction. That just gives us a much more clear indication that we're only looking at horizontal acceleration. Okay? So let's go ahead and write out our net force equation here. F net is equal to right forces minus left. Okay, and this just tells us we're looking only at the net force in the x direction. Okay, I'm kind of adding subscripts here to just make sure it's really clear to you. You don't have to include all those subscripts if you don't want to. I'm just trying to make sure that you understand we're only looking horizontally here. Okay, does that make sense? You can choose to include those if you want. You don't have to. Okay, so F net in the x direction, we're going to take rightward forces minus leftward forces. So what rightward forces do we have? F what? Yes. Yep. F applied X. So F applied in the X direction. Do we have any leftward forces? No. So you can either write a minus 0 so that you know you accounted for them, or you can leave that minus 0 off. It does not make a difference at all. Okay? So now let's go ahead and do our substitution here. What do we also know that F net is equal to? Mass times acceleration. So mass times acceleration is equal to F applied X. Okay. Now, can we solve for F applied X? Yeah, all we have to do is break down that component. So let's go ahead and do that. When we're solving for F applied X, we'll take 2,000 times cosine of 60 degrees. And that gives us a value of 1,000 newtons. So now we can go ahead and plug that in over here for our F applied x. We're solving for mass, so we're going to leave that as an m. That's what we're solving for. That's a variable we need to save. And then we know our acceleration in the x direction, in the x direction is 10 meters per second squared, which means the mass of our car is 100 kilograms. Okay, so maybe it's like a... Go ahead and get this one written down, and then we'll start talking about what we need to look at here. Okay, so let's go ahead and start with our free body diagram. Sam, can you give me one force that's acting on it here?
200 newtons to the horizontal at 30 degrees.
Yep. Okay, Nick, can you give me one? Gravity. And what do we label gravity? F sub g. Good. And Katrin, can you give me one more? F sub n, the normal. Normal. Okay? So that's it. We don't have any, it doesn't tell us anything to include friction, so we don't have to. I want you to, there's one very, very important line in this question. Okay, and here's our very important words. Okay, it says the machine begins to slide. So we're applying a force that's both vertical and horizontal. We're trying to lift, or we're trying to pull this machine upward, yet it begins to slide. So that means we're dealing with horizontal or vertical acceleration. Horizontal, right? This object does not lift it off the ground. Okay, it's not actually being lifted off the ground, which means we still have a normal force. We still have gravitational force. We still have that applied force in the y direction. We'll still have the components here. Okay, so F applied y and F applied x. We still have all these forces acting, but in the vertical direction, is there any acceleration? No, that's important. And that comes just from this line right here. Okay, it begins to slide. That's got to click with us that, okay, it's not leaving the ground, which means it's not accelerating in the vertical direction. Okay, it's only accelerating in the horizontal direction. So we want to find the normal force. Is that a horizontal or a vertical force? Vertical. So that's what we're looking at here. We're only concerned about the vertical forces. So let's write out our F net equation for vertical. Okay, and that's upward forces minus downward forces. Okay, upward forces minus down. So, Peyton, can you give me one upward force that we have? Good. F sub n. Raven, can you give me another one? So F applied y. Good. And then, do we have any more upward forces? Nope. What's our downward force, Michaela? F sub g. Good. Okay. So this is our net force equation. All of our upward forces minus our downward forces. We know that the net force for this particular system in the vertical direction is equal to what? 0. Our net force here in the vertical direction is equal to 0 because it's not accelerating in the vertical direction. Essentially, it's at rest in the vertical direction. And the net force of anything at rest has to be 0. Okay? So that means 0 here is equal to F sub n plus force applied y minus F sub g. Okay, now we can go back and start looking at numbers and plugging in some numbers here. So we can solve for F applied y by taking 200 sine of 40, and I got 128.6, I think, yeah. Can we also solve for F sub g? Yeah or no? Yeah, we can because we have our mass and we know gravity. F sub g is equal to mass times gravity, which is equal to 50 kilograms times 9.8. Okay, so now we just plug in our numbers. 0 is equal to F sub n plus 128.6. It's positive because we're pulling it in the upward direction. Gravity is acting in the downward direction, so we subtract that out. We'll move that to the other side to make the normal force equal to 361.4 newtons. Okay? Okay, so page 93. This tells us two boxes are connected by a cord. Okay, here's our cord in the middle. They're resting on a frictionless table. Their masses are listed here. There's a pulling force to the right of 40 newtons. We want to find the acceleration of each box and the tension of the cord. Okay, and we want to find the tension of this cord right here. Okay, so get written down what you need to, and then we're going to start looking at some free body diagrams and some equations here that we need to solve for acceleration and tension on each of these objects. Okay, so let's start with the object on the right first, our mass 1, or our first object, which has a mass of 10 kilograms. Okay, I'm going to draw our free body diagram starting right here. So we've got a force pull to the right, F sub p they've labeled it. It has a magnitude of 40 newtons. Okay, we've also got a force going this direction, and what would that force be called? What would we name that? F sub t for tension, right? It's the cord. Sorry, that's not in a very good spot. Okay, for tension, because that's our cord that's pulling to the left. And I'm not drawing these to scale quite correctly just because I didn't want to write over those numbers too bad. What vertical forces do we have on our object? Normal force and gravity. Good. We're resting on a table, which means we have the normal force and it can't escape gravity. Okay, so there's our free body diagram of our first object. Our second object also has force due to gravity and the normal force. And it's only got one horizontal force this time, which is also the force of tension. Okay, it's that cable that's pulling. Is the tension in that cable going to be different depending on which box we're looking at? No. Okay, that tension, F sub t, is going to be equal for both boxes. And that's important. That's really important for us. Okay, so F sub t is equal in both boxes. Okay, so let's go ahead and start looking at our net force equations here for each of these objects. Are either of our objects accelerating in the vertical direction? No, which means we only care about the horizontal forces. Okay, we know gravity and the normal force are staying the same for both of those. It's not accelerating in the vertical direction at all. So we're going to look at, let's look at our first object, and we're going to look at F net of our first object here. Okay, and if you really want, you could put a little x there also. So you're telling me we're looking at the net force of the first object in the x direction. Okay, all of those subscripts have a meaning, so you can add as many or as few as you like to keep yourself organized. Okay, that's up to you. Okay, so F net in the x direction for the first object, which is this one right here, we'll take our rightward forces minus our leftward forces. Okay, so our rightward force in this case is F sub p, right here. Our pulling force minus F sub t, right, our tension force. Are we clear with that? Rightward forces minus leftward forces. Okay. Let's talk about the net equation for our second box. Again, you don't have to label all of these subscripts. Okay, that's just telling me that I'm looking at net force of the second object in the x direction. Okay, you do not have to include all of those. It just depends on how much you need to keep yourself organized. Okay, so our rightward forces in this case are the tension force. Do we have any leftward forces on our second object? No. So you can put a minus 0 if you want, or you can just leave it off. Okay, those have to be equal. So what do we know about the acceleration of our boxes? Are our boxes going to accelerate at different rates? Won't these boxes have equal acceleration? Won't both of their accelerations be equal? When we start moving, they're going to be moving at the same rate. One's not going to move faster than the other. Okay, so that means that A1 equals A2, right? Or both of our accelerations are equal to each other. Okay, so we're going to kind of start manipulating our equations here and starting to do some substitutions. Okay, so I'm going to look at our simplest equation first, which is this. What can we substitute for F net?
M times A.
M times A. So I can take mass of object 2 times the acceleration and set that equal to force of tension. Do I need to label them A1 or A2? No, because they're equal to each other. Our accelerations will be equal. Okay? So mass of our second object times its acceleration is going to equal our tension force. Okay? What about my first equation now? Can I do any substitutions in that first equation? I can take M1 times A equals our pulling force, which is 40. I can go ahead and put a 40 in there, minus F sub t. And what do we know F sub t is equal to? M2 times A. Okay, so let's take a step here for just a second. We substituted mass times acceleration in for F net. Okay, and this is of our first object. Our pulling force is equal to 40 newtons because that's what the problem gave us. And F sub t, since it's equal in both of those boxes in both of our situations, we set it equal to M2 times A, so we substituted that in right here. Okay? Any questions? So now what other numbers can we start plugging in? We know both of our masses, so we can plug those in. Okay, so M1 times A, which is 10A equals 40 minus 12A. So to solve for A, I'm going to add that 12A to the left side. I get my value for acceleration equal 1.82. Do we agree? What questions do we have about our substitutions that we did? Nothing? Can you follow it? Okay, I know this will be difficult to do on your own, but I want you to see the important thing here for you to see is that the tension force in both of those is equal to each other. That's our connector between our two objects. Okay? So then to solve for tension, we're going to take F sub t, and we can just plug it right in with our acceleration we just solved for times m2. Right? We want to solve for the tension of the cord, so we'll take 12 times 1.82, and we get a value of 21.82 newtons. Okay, we've got some object. Okay, there's an object hanging, a cable between them, and a second object. Okay, so here's our 1,200 kilogram and our 7,000 kilogram. Okay, each of these has its own free body diagram. So for our first object, our upward force will be a tension force, and our downward force will be gravitational force. Okay, our free body diagram for this second object looks exactly the same. F sub t and F sub g. Oops, I'm sorry, I did that wrong. I'm sorry. No, never mind. No, I didn't. We've just got another tension force pulling downward. But we don't really care about this guy. Okay, because all we're looking at is the tension in this section between.
So they're two different tension forces then?
I don't remember. No. I did it wrong. I drew it wrong. I did it right the first time. I'm second guessing myself. This is it. This is right. Just like this. We're going to look at the tension in this cable and the tension in this cable. I'm sorry, I didn't mean to confuse you. Those are two different tension forces. Yes, I'm sorry.
Should we label them like that?
You can, yeah. F sub T1 and F sub T2, or F sub T top and bottom, or whatever you want to label them as. That was my fault. Okay, but since they're two different sections and they have two different masses hanging, they won't be the same. Okay, so that's what I get for second guessing myself. Let's look at the top tension first. We're going to look at this top section of cable first. Okay, we're going to look at top cable first. Okay, our net force equation for this top cable, F sub T minus F sub G. Do we have any sort of acceleration of our system here?
Yes.
2.1 meters per second. Is it going in the positive or the negative direction? Negative. It's lowering. So we need to take a negative 2.1 as our acceleration. Okay, so let's start making some substitutions here. We know F net is equal to mass times acceleration. We're solving for our tension force, and we know that F sub G is equal to mass times gravity. Okay, so if we're looking at the top cable here, what mass are we looking at that's hanging below it? How much mass is hanging below this section of the cable? Yeah, all of them, both of those weights. We have to account for both of those weights that are hanging below it. Okay, so our mass here, we're going to take 1,200 plus 7,000 times negative 2.1 equals FT minus 8,200 times 9.8. Okay, since we're looking at this top cable, we've got to look at the mass that's hanging below it, all of its mass that's hanging below that cable. Okay, so it's both of them. And it told us the mass of the cable can be ignored, so we don't care about this little mass of this cable in the middle. Okay. Okay, is that what you got for this top cable? 63,140 newtons. Okay. So now let's look at the bottom cable. The only thing that changes here in our whole problem between the top and the bottom cable is the mass, right? Because what mass is hanging below this section of the cable? Only the 7,000. So we're only caring about the 7,000 kilogram mass. So I'm going to just tweak some things here. Our equation stays exactly the same because our free body diagram looks the same. Only now we're looking at the bottom cable. So when we take mass this time, we're going to take 7,000 times negative 2.1 and 7,000 times 9.8.